So before we plunge into our last fundamental principle, which is the angular momentum principle, we're going to take today and probably part of Wednesday to sort of consolidate some things by considering a class of phenomena that will require us to use both the momentum principle and the energy principle simultaneously in order to analyze what's happening. So this will really be the first time we've had to apply two principles in order to solve one problem. And the class of phenomena we're going to be talking about are collisions. A collision has a technical definition in physics. So it's a very brief interaction on some time scale of interest, and it involves very large forces compared to other forces. So in fact, usually what one does you take the system to be all colliding objects, and the idea is that the forces between the objects in the collision are so strong that during that brief period any external forces are negligible. So if we throw a ball at the wall, during the period where it's interacting with the wall, the gravitational force doesn't have a chance to do very much. It's a brief interaction, and the interaction with the wall is so strong. So the virtue here is that then we can so forces due to objects outside the system are nearly zero. Now, usually when you think about a collision, you think about two things actually making contact, but it doesn't actually, things don't really even have to touch each other in order to act strongly enough to be considered a collision, because they can interact through an electric force, gravitational force, or a magnetic force. And so the atoms might not actually touch each other, but you can get a brief interaction. And the interaction could actually be attractive as well as repulsive. So it doesn't have to be a repulsive interaction. The virtue of considering all of the objects that we're interested in to be the system is that then writing down the momentum principle and the energy principle is really simple, because we get, so P final for the system is going to be equal to P initial plus 0, and E final is going to be equal to E initial plus 0. So there are basically no external inputs to the system during this brief collision. That doesn't say that momentum and energy can't change, or more specifically, because momentum can flow from one object to another within the system, energy can not only flow from one object to another, but we now know that energy can go from kinetic energy into internal energy of some kind. It could just get hotter, it could deform, it could vibrate or rotate or whatever. So some sort of complicated things can be going on. And it's not always the case that change in internal energy is 0. And that means the total kinetic energy may also change. So we have to actually think about the physics in order to decide whether kinetic energy is flowing into internal energy. We need to actually think about the process and think about the situation. There's not exactly a prescription, but some of the things that are an indication that internal energy of a system is changing is it gets hot, so thermal energy increases. Things could deform. Things could stick together. Things could vibrate or rotate. So these are all ways in which all things that reflect a change of internal energy. And there are these technical names for we classify these collisions by whether the internal energy changes or not, and therefore whether the kinetic energy changes or not. So if there's no change in the total kinetic energy and internal energy, we call this elastic. And we're talking between final and initial. So if you throw a tennis ball at a wall, it compresses when it hits the wall, but then it expands back out and may rebound with almost the same speed it had going in. And so that's and if there is a change in internal energy and kinetic energy, we call that inelastic, and these are some of the indicators that something is inelastic. So what we're going to do is just think about a simple collision between two objects that are more or less identical, two of these little carts. They're going to collide head-on. They have the same mass. So that's pretty much the simplest possible case. And see what we can predict that the behavior of this system is going to be, and then we'll try it. To start out with, let's actually remind ourselves about one thing that we need to be careful about, which is thinking about momentum and momentum changes. We've been talking about energy for a long time, so let's think about momentum for a minute, just remind ourselves what's happening. So consider the situation where you throw a ball at a wall, it collides with the wall, and it bounces back, and to the accuracy which we measure it, it comes in with a speed of 6 meters per second, and it goes out with a speed of nearly 6 meters per second. So the question is, consider the x component of momentum of this ball. What's the change in the x component of momentum of this ball that hits the wall and bounces back? That's not a unanimous answer, is it? It's not. So we need to think about momentum a little bit more. So let me say this is one you need to be able to do. So let's review. We have, with the usual coordinate system, the initial momentum of the ball would have been 0.1 kilogram times 6 meters per second gives us 0.6 kilogram meters per second in the plus x direction. And the final momentum is what? Negative 0.6. 0.00 kilogram meters per second, and the change in momentum is P final minus P initial, and it looks like delta P would be negative 0.6 minus 0.6 is negative 1.200 kilogram meters per second. So the change in the x component of momentum wasn't 0. There really isn't a substitute for actually thinking about P final minus P initial. Do you have any questions about that one? Now, what is it that was 0? What change was 0? Magnitude of momentum. We'll see about energy in a minute. So in the same, if we take everything, if we're going to consider colliding objects as the system, that means that we have to include not only the ball but the wall. But the wall's pretty strongly connected to the Earth. It's sort of sticking out of the Earth, in fact. So what was the change in the x component of the Earth's momentum in this collision? If we take the system to be the ball and the wall and the Earth, everything in the, or the wall connected to the Earth, so if you change the momentum of the wall, it's going to change the momentum of the Earth because it's rigidly connected to the Earth. Okay, well, most people say that it was 0, but some people say it's plus 1.2 kilogram meters per second. What would the momentum principle tell us? If the system is the ball plus the Earth and the wall, well, yeah. I mean, if the momentum of the system, so what's the system? So for the system of ball plus Earth and the wall, what does the momentum principle say? It says P final, P initial plus no negligible interactions with the rest of the universe during this period. And so initially we just had the momentum of the ball, which was 0.600 kilogram meters per second, and the momentum, we're in a reference frame, we're standing on the Earth, so we say that the momentum of the Earth relative to that location is 0. Looks like, so the total momentum finally had better add up to that. So if we have a negative 0.600 kilogram meters per second for the ball, what do we have to add to it to make, so this is the ball initial, this is the Earth initial, this is the ball final. What must the final momentum of the Earth have been? Yep. So we have to have a plus 1.200 kilogram meters per second. So it changed from 0 to plus 1.2, so answer 3 is correct. Now, why do you want it to be 0? Just because the Earth is big, massive? Would you notice a change in the Earth's momentum of this magnitude? No, you wouldn't. Okay, it would not be a noticeable change. But according to the momentum principle, it must be happening. So there must be lots of infinite, very unperceptible changes in the Earth's momentum due to all these things interacting with it. Okay, so we're gonna actually believe the momentum principle today. We're gonna use the momentum principle. We're gonna use the energy principle, and we're gonna see where it takes us. So here's the system we're going to analyze. We are going to predict what would happen if we take this cart, give it some initial momentum, and let it collide with this identical cart here. We're going to predict what the final momentum of these two objects is going to be, how they're going to behave, and we're also going to look at what happens to energy. Okay? And then we're going to try it and see if our prediction was right. So let's see if we can work it out and predict what we're going to see when we actually do the collision. So given what we've just said, what do you think we ought to choose as the system? Two carts. Okay. So we have two identical carts. The system, both carts. And we'll draw a little diagram to remind us of what's happening in the initial situation. This one is going to be at rest. So we'll talk about x components of momentum. So this is cart 2, P2x initial is 0, and P1x initial is whatever it is. So that's the initial situation. And in the final situation, we've got these two carts, 1 and 2, and we want to know, so let's write it this way, P2x final and P1x final. That's what we want to know. And we're just going to use the momentum principle in this form for the delta t of the collision. P final equals P initial plus 0 external inputs, and see what we get. And we can just work with x components. It's simpler. So let's start with the momentum principle. So we have the final momentum of the system. Well, let's only talk about x. So px final, px initial. So initially, what do we have? We have P1x initial for that cart number 1, and we have 0 for cart number 2. And final, well, we've got whatever these things are. So P1x final, P2x final. So that's the momentum principle. Now, the only thing we know is this quantity would be known. We know it's non-zero because we're giving this some momentum. We could measure it. So if we actually got a number for it, then we should be able to get a numerical solution. But we have a problem. What's our problem in trying to solve this? How many unknowns do we have in this equation? We have two unknowns, and we've only got one equation. So we don't have enough information to solve with the momentum principle alone. So it's all we know is the sum. So we better try the energy principle. And we're going to make an assumption here. Assume that this is elastic. So change in internal energy is 0. And so we have E final is E initial plus 0. And so if we're assuming that the internal energy of these carts doesn't change, meaning they don't deform, they don't start vibrating, they don't get hot in the collision, they don't stick together, then we can actually just not write the internal energy terms in this equation, or we could write them and say there's no change. So here are the things we have to consider. The initial kinetic energy of cart 1 plus the initial kinetic energy of cart 2 plus the internal energy of cart 1 plus the internal energy of cart 2. And over here we've still got all the same things. We've got the kinetic energy, final kinetic energy of cart 1 and the final kinetic energy of cart 2 and the final internal energy of cart 1 and the final internal energy of cart 2. And since we're saying elastic, we can say that there's no change in these things. And so we have a much simpler equation, which is K1 final plus K2 final is K1 initial. And what do we know about the initial kinetic energy of cart 2? It was 0, so we can, that's 0. Now, it still sort of doesn't look right because we got momentum up here and kinetic energy down here, but so it looks like we have 4 unknowns. So how's this going to work? You can write them both in terms of velocity or speed, can't you? So in fact, we can write kinetic. So remember that a half mv squared, which is the kinetic energy at low speeds, is also can be written as the magnitude of the momentum squared over 2m. So we can write this as, let's write it up here, P1 final squared over 2m plus P2 final squared over 2m is P1 initial squared over 2m. And there should be x's here because that's the only thing we've got. Okay, so now we have 2 equations and 2 unknowns. And we can do the standard things one does to solve them. So we'll use substitution. We have this P1 initial, P1 final, P2 final, but notice here that we can write P1 initial in terms of P final here. So we can use that substitution. We can take this expression and plug it in there, which is one of the standard ways to solve 2 equations and 2 unknowns, right? So let's rewrite this equation here. We can multiply. We got this from the energy principle. We can multiply through by 2m, so we get P1x final squared plus P2x final squared is equal to P1 squared, but we have this expression, so we've got P1x final plus P2x final quantity squared, just substitution. Okay, so it's just algebra. Now we'll just multiply this out. So we get P1 final squared plus P2 final squared is P1 final squared plus 2 times P1 final, P2 final plus P2 final squared. That's an odd looking equation. Because we got this term, these terms on both sides of the equation, right? So we subtract them from each side. And we're left with 0 equals 2 times P1x final, P2 final. The product of the final magnet, the product of the x components of the final momenta is 0. Does that tell us anything interesting? So one of those things has to be 0, doesn't it? And there are two possible solutions here. Either that could be 0 or that could be 0. So here are two solutions. Either P1 final is 0 or P2 final is 0. So if P1 final is 0, what does that correspond to physically? Okay, right. So the first one just stops and the other one goes. What does this one correspond to? No, it can't bounce back because that. It actually sounds like car 1 goes through car 2, doesn't it? That's exactly right. Mathematically, that's what it says. It just goes right through and keeps on going. Now, the algebra doesn't know that that's not a possibility, but car 1 would just have to go. Okay, so we don't expect cart 1 to go through cart 2. We think that's not probably what's going to happen. So what we expect is cart 1 stops dead and cart 2 moves, right? Let's see if it happens. So it looks like we were right. We'll do it again. Let's try that one more time. It wasn't supposed to bounce back. There we go. And what did it look like, the speed? How was the speed of the second cart compared to the initial speed of the first cart? Looks the same, doesn't it? So all the momentum just got transferred to the first cart. Now this is a special case because this was a collision of identical objects hitting head on, one initially at rest. So there were a lot of conditions on that. But notice that we had to use two principles to make a prediction of what was going to happen. And so it looks like that was our assumption of elasticity in the collision, that kinetic energy didn't get converted to internal energy. It just stayed as kinetic energy and flowed around in the system, was justified because our prediction matched what we saw. Let's think about a different situation where the collision is inelastic, meaning kinetic energy gets converted into internal energy. And we'll make it as inelastic as we possibly can by having the carts stick together. So certainly some energy is required to make things stick together. Bonds have to form, and then things can vibrate. And the way this is going to happen is that these carts have little Velcro dots on the ends. And so if the Velcro dots connect, the carts can stick. And you can see that there'd be some play in here. There could be some vibration in the Velcro. The hooks have to engage. So there's certainly some energy going into that. So a collision in which things stick together is not elastic. It is inelastic. Some energy, kinetic energy, gets lost. By the way, notice that this collision we were doing, this elastic collision in this case, did the carts actually ever contact each other? Did you hear them go thunk? Did you see them touch? I don't know if those ones up in front, did they actually make contact? Did you see that? Well, look again. Yeah, not quite, because they've got magnets in the ends that are repelling each other. So in fact, they never did touch. So that was a collision that involved a strong interaction, happens to be repulsive, but the things don't actually have to make contact with each other. These distance forces will do it just fine. Okay, so let's predict what we're going to see for an inelastic collision. So what we're going to have here is same initial situation. One card at rest. So that's P1 initial. But then they're going to stick together. And so what we want to know is, so this is still 1 and 2. So we want to find several things about it. We want to find the final momentum. So we want to find the final momenta. We want to find the final kinetic energies. And let's find the final speeds of these things too. So what do we write down for the momentum principle? Yep, P final equals P initial. What's our system? Both carts. Okay, so we have and so initially this is P1x initial plus 0. And we have P1x final plus P2x final. But there's a constraint here. What do we know about the relationship between the momentum of 1 and the momentum of 2 in the final state? They're the same. They're constrained to move at the same speed, so the momentum must be the same. So we can actually write this as 2 times P1 final as P1 initial. And that actually gives us 2 MVX final is MVX initial, so the final speed should be half of the initial speed. We didn't need energy for that, but we're going to need to think about energy to see where the kinetic energy went. So our prediction is, so far, that they're going to stick together and move at a speed that is half the initial speed. Okay, so let's see if that makes sense. Well, they didn't stick. Come on, stick. Well, it's certainly slower, isn't it? It's plausibly half the initial speed. We don't have a... If you had a motion sensor, you could tell it. This Velcro seems kind of worn out. Let's see if this Velcro is any better. There we go. Okay, so plausibly half the initial speed. So our okay, well, we haven't said anything about energy though yet. So let's think about the translational kinetic energy. So what was the initial translational kinetic energy of the system? Well, it was just half mv initial squared, right? And the final translational kinetic energy is going to be the energy of one plus the energy of the other, right? So we're going to have the energy of one cart is a half mv final squared, and we have two carts. So we have 2 times half m v1 final squared. But we know that v final was half of v initial. So that looks like 2 times a half m times v initial squared, half v initial quantity squared. And so when we get all done, that comes out to a quarter, because these twos, yes, so a quarter. So it looks like the final translational kinetic energy is only half as big as the initial kinetic energy. So we lost some kinetic energy. The momentum was the same, but the energy wasn't. It's at squared. So what happened to it? It's internal energy. So in fact, this must be the increase of internal energy must be that. So we can write the energy equation. We have E final is E initial, so we have initial translational kinetic energy plus initial internal energy. We have final translational kinetic energy plus final internal energy. This is a quarter mv initial squared. This is a half mv initial squared. I'm dropping subscripts here. And so it looks like the final minus the initial internal energy is equal to a quarter mv initial squared. So half of the original kinetic energy went into the internal energy and half is still present. So that's very inelastic. Kinetic energy decreased. And where did the energy go? Well, this Velcro's poking and vibrating and maybe even getting a little hot, but that's a big loss, yeah. It's you subtract 1/4 from both sides, and you subtract the internal from both sides, and so you get delta E internal. So that's change in internal energy is a half of the initial kinetic energy. Okay? Just 2 algebra steps at once. Let's think about another head-on collision. Let's see what we can say about this. So consider the following situation. You have a squishy clay ball and you have a baseball, and you and your friend throw them up in the air in such a way that they collide in midair and the clay sticks to the baseball. And so we know the initial momentum of the clay and the initial momentum of the ball. There's some number there. And we know the final momentum of the clay plus the ball. Which of these equations correctly describes the relationship between the initial and final momenta of this system? So what's going to happen? Is the final momentum going to be... This actually isn't a trick question. This is a question asking you to apply a physics principle. So it isn't a guess what happens question. It's a what do physics principles say about this situation? Okay, so 54% says P2 is P1 clay plus P1 ball. A small vote for greater. A fairly big vote for less, and might need to know some other things. Okay, but what do the physics principles say? We're talking about momentum here, so what principle are we going to use? The momentum principle. And yeah, it's not and what is this? Is this a collision? It's definitely a collision, isn't it? So what are we going to take as our system? Both objects, clay plus ball. So system is and if it's a collision, during this collision, what are we assuming about interactions with the surroundings? Negligible. Negligible. So therefore, we've got P final of the system, P initial of the system, plus F due to the surroundings, delta T. That's negligible, so that's 0. This is the final momentum of the system has to be equal to the initial momentum of the system. It's really straightforward. So we have, what do we got? The P2, this is P2, and that's P1 clay plus P1 ball. There's not that much to it. Now, what's different about momentum and energy in collisions? Yeah, energy can change and momentum can't, because there's no internal momentum. There's no way for momentum to go inside the ball. Momentum is momentum. Energy has all these different forms. So it can be kinetic energy, it can be potential energy, it can be this sort of detailed internal energy motion. Energy can flow, slosh around from kinetic to internal, kinetic to potential, springs get compressed in one. There's only one kind of momentum, and it's sticky. Momentum is like glue. Once you've got it, it's like being it in tag. Once you've got this momentum, once you're it, the only way to get rid of it is to give it to something in the surroundings, give it to someone else. So it's got, these things have this momentum. They aren't able to give it away, so because they're not interacting with anything else, so they're stuck with it. So momentum in collisions is really simple. Final momentum of the system is initial momentum of the system. It can't be more simple than that. Energy's not simple. Energy can be more complicated, right? So yeah. So, well, energy is a scalar, which is really nice. So we decided that for the system of clay plus ball, the final momentum had to be equal to the initial momentum. What's true of the kinetic energy of this system in this particular situation? Okay, so now a fairly large majority say that the final kinetic energy of the system is actually less than the initial kinetic energy of the system. What indications? What do we know about this interaction that suggests that to us that this would be the case? It's inelastic, meaning they stuck together. That's about as inelastic as you can get, and so there's lots of interaction going on, lots of bonds being formed. The clay is deforming and stretching, so it's like a spring. It's being stretched. Eventually, it might even get hot. So it's inelastic, and that means that's just a fancy word for kinetic energy gets converted into internal energy, isn't it? And so the final kinetic energy is less. That's what we saw here. Okay. questions about that.